Hello and welcome back to Calculus 1. The topic of the day is approximating area under the curve. So we are going to take a look at a way to find the exact area, and then we are going to tamper with the function a little bit and then see that it's not easy to find the area and then approximate it instead. And then we are going to actually take that approximation to the infinity and make it exact. So we're going to go the full circle. So what do you know so far? Hopefully you know that area of the square is a squared, right? Rectangle, a times b, area of the triangle, 1/2 base times the height, and then a whole bunch of other shapes. Area of the circle, anyone? Very good. So all of these areas, and you memorize these formulas, right? For the square, area is a square. For the rectangle, area is AB. For the circle, area is pi r squared because you have just a radius r. And speaking of the devil, very good. And does anyone know what the area of the ellipse is?
12.
Did you just say 12? You like to walk.
I do. I need to. I only lose a couple pounds, so I'm trying to get my steps in.
So what do we have here? Anyone?
It's two different radiuses, so can you just
Okay.
use your nose separate?
Wouldn't you agree that this is like a square over here? So you have radius one way, radius other way, and this would be like a rectangle?
Yep.
Yeah. And then you take the pi to smooth it out, to curve it. So that's it. So they're actually pairs like that. Triangle. One-half base times the height. Trapezoid. A plus b over 2 times the height, and so on. So, and this goes on and on and on for a whole bunch of different two-dimensional shapes. So you memorize these. And these are exact formulas. They give you exact areas. But now, what I'm interested in is, what is the area under square root of x from 0 to 4? So what is the area in here? Now we don't have a geometry equation for this. And if you look at this graph from sufficiently far away, this might look like a triangle, right? So I would say it is okay for you to say, you know what? I am going to make this into a triangle like that. And then we know that this height over here is 2 because the point on top is 4, 2, if you compute 4 in a square root function. So the area is approximated by 1/2 base times the height, which is 4. So we would approximate this one that way. But then you see all of these area here, right? And all of that area there is error. So you know that your estimate is below. And it looks like a significant amount. So it looks like there is a lot of error in your calculation. And maybe we can do better. And we can. So what I'm going to do instead of creating this one triangle, I'm going to take this function square root of x between 0 and 4 and cut it into these what appears to be rectangles. And then I can say create rectangles where the left corner of each one is going to give us the horizontal line to create a rectangle. So there is this, 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 and this. Now the numbers over here are 0, 1, 2, and 3, right? 3, 4. Now if you observe the first rectangle, its area is 0 because there is no height to it. The second rectangle is 1, and so on. So let's compute area of each of the rectangles. No coffee. The heights, the y values over here, are going to be points 1, 1, 2 root 2, 3 root 3. We don't need the one at the end because it's not creating a rectangle. All the rectangles are to the right of the point. So the last point 4 doesn't have a rectangle to its right. So if you take a look at the 4 rectangles here, the area, the exact area is approximated by 1 times 0 plus 1 times 1 plus 1 times root 2 plus 1 times root 3. What is this 1? 1 is going to be the width of each one of the rectangles. And 0, 1, root 2, and root 3 are heights of each one of these guys. So when you compute this, you see that you have 0 plus 1 plus root 2 plus root 3. And you can use Abacus to figure out the value of this calculation, right? And keep it to 1 decimal point or 2 decimal points. I really don't need a 12 decimal precision on things like this. So 1 plus square root of 2 plus square root of 3 is 2.93. Now you're looking at this and you say, well, hold on. There was a lot of error here. Can I redo this problem in a better way to hopefully reduce the error? Well, here is the same problem, but now I am going to draw the rectangles to the left. So the first rectangle goes this way, second rectangle goes this way. And I still have my 1, 1, 2 root 2, 3 root 3, and 4, 2 at the end. So we have our heights. The width is still 1 unit each. So now area is approximated by 1 times 1 plus 1 times root 2 plus 1 times root 3 plus 1 times 2. So I have 1 plus 2 is 3 plus root 2 plus root 3. And that's going to give us 493. Now we have error that it's on the opposite side. So now we are overshooting with our estimate. So in the previous example, the area is what you see in white, and the red stuff is error. This is the same problem, but done with the rectangles that are on the outside, and we still have error, but now we are overshooting. So what I can conclude from these two pictures is that the true area is in between these values, 293 and 493. I don't know how much. Now, you know, we can average these values, right? And come up with the 393. Remember how we did the triangle? 393 and this is 4. It sounds like it hovers over that. Now the question is, can I do better? Yes?
Can you do a quarter of an ellipse?
Well, yeah. Yes, I can. But now I want to see if I can use this method to get the better result. So we do the same problem again. But now, instead of partitioning for each unit, I can partition at each half unit. So I have better resolution. All right? The way you make your screens better is to make smaller pixels, right? And put more of those pixels in. You know, you ever heard of a DPI? It's a dot per inch. Right? That's the important thing. So let's do the same problem, but now I'm going to increase the resolution. What does that mean? Well, I have my square root function, and now I'm going to, instead of, right, I'm still going to have 1, 2, 3, and 4. But now I'm going to put double amount of rectangles. And now I have 1 half, 3 half, 5 halves, and 7 halves as well. This creates 8 rectangles now. And if I go like this, I hope that by comparing the picture on the top and the picture on the bottom, I hope you see that there is less red on the picture on the bottom. There's less error. So when I approximate the area using the rectangles, the picture on the bottom, it's going to be closer to the exact area. Now, you know there's no free lunch, right? That means that something else is going to give. And that is definitely calculations. because now, instead of calculating 4 areas, you are calculating 8 areas. So you double the number of rectangles and you effectively double the number of calculations. Plus adding the annoyance of the square root of 1/2 and square root of 3/2 and square root of 5/2 and so on. So everything is doubled now. So now my area is, please note that each one of these areas now has 1/2 as length. So I have 1/2, which is the width, times the square root of 1/2, which is the height, plus 1/2 as a width times the square root, plus 1/2 times the square root of 3/2, plus 1/2 times the square root of 2, plus 1/2 times the square root of 5/2. Congratulations. Plus 1/2 square root of 3, plus 1/2 times the square root of 7/2, plus 1/2 square root of 4, which is 2. You see 8 calculations. So each rectangle has the height when you compute the point at which you are observing in the original function. Now we need to compute all of this. The fastest way to compute all of this is clearly to factor out 1/2. Because why would you compute all 8 of these if you can just add and then multiply once? So the fast way to compute this is to kick out 1/2, and then you have your square root of 1/2 plus 1 plus square root of 3/2 plus square root of 2 plus square root of 5/2 plus square root of 7/2, no, square root of 3 plus square root of 7/2 and plus 2 at the end. And now you compute all of this. Oh, I should have said area is approximated by. So we have a square root of 0.5 plus 3 plus square root of 1.5 plus square root of 2 plus square root of 2.5 plus square root of 3 plus square root of 3.5. So I have 1/2 times 11.53, and when I multiply these two, I get 5.76, 5.77. Something is wrong over here. This is a little bit too high. Two, 2.5, 3, 3.5. Well, that's what we have. So area is 577. I don't think I made any mistakes. I plugged everything correctly in the calculator, so you have the same? All right. How do I get better precision? Yep, exactly. Put in more rectangles. So what do you think happens if I keep adding rectangles to infinity? If with every passing, every time you add rectangles, your result gets better. Your result gets closer to the exact area. What happens when you use infinitely many rectangles? Anyone? Yeah, you hit the exact area. Think about it. If you have the function and you're going to 4 from 0. And there is the first rectangle at 0. At each point, you are going to draw an infinitely thin rectangle. And the trick is, since you have to put infinitely thin rectangle, you will actually have to put infinitely many of those. That will actually, line by line like this, cover entire area. So that's what we have for our concept for this. The concept is the more rectangles you use, they get thinner. The more rectangles you use, the less error you have, the more precise your estimation of the actual area is. Now I need to talk about some of the, okay, so if we use infinite number of rectangles, we get exact area. So the more, the smaller the delta x, right? More delta x's you can fit, so you're getting better answer, better approximation. So let me one more time draw the same function. And talk about some notation and other. So I picked to have equal spacing. And if there is equal spacing, we can call that delta x, because we know that delta x is x2 minus x1. So the formula for delta x is going to be b minus a divided by n. You have your a and you have your b for the start and the end of the interval at which you want to approximate the area. And then is the number of rectangles. So this over here is the interval, and this over here is the number of rectangles. Number of rectangles. You must know this formula. Now, didn't we cover in differentials that dx and delta x are the same thing? Yeah, right? So that's the dx in the integrals, but we'll get there. So now, in this case, delta x is equal to x to the n minus x to the n minus 1. So just to, the way to see this formula and to read this formula, what is the delta? So we have x, let's say x3 minus x2. Like that would be the idea. Or x to the x7 minus x to 6. Because the index over here, it tells you that whatever the first index is, the second index is minus 1. So if I start with a 3, the next one is 2. If I start with 7, the next one is 6, and so on. So which function should we look into now? We looked only at x, square root of x. Do you have any other suggestions? X squared? Okay. So we're going to approximate the area under the function x squared on which interval?
0 to 5.
0 to 5. And how many rectangles do you want to put in this thing?
Oh wait, we should do negative to positive. Like negative 3 to 3.
You want negative 3 to 3. Okay, fine. How many rectangles are we going to use? Let's use anything other than that. 5? Oh, 5 is an awesome number. You're going to hate this. So these are the specs that you get. We are looking for area under the curve, which is x squared. We are looking for the area from negative 3 to positive 3, and we want to use 5 rectangles. Okay, well, I know that in my formula for areas, approximating areas, I have delta x times, and then this is f of x0, let's go with the f of a. That's the first point. And then we have plus f of x1 plus f of x2 plus f of x3 plus dot dot dot, and the last one is f of x or f of b. This is technically a formula for you to compute these things. If you distribute dx, you see that it's delta x is the width. So it's width times the height, width times the height, width times the height. So each one of these separately produces area, and then and then you add them all up to get the overall value. So what's your delta x? Delta x formula is boxed above. It's 3 minus negative 3 divided by 5, so we have 6/5. So delta x is 6/5. I'm going to draw the partition for this. Pay attention. The world starts at negative 3. Because that's A. All I need to do is to keep adding 6/5. So negative 3 times 5 is negative 15, and then 6, so it's negative. So, hold on. So negative 3 plus 6/5, that's negative 15, and the 6 is negative 9/5. Add another 6/5. When you add 6/5 to this, you get negative 3/5. Another 6/5. No, something is wrong. This is, or maybe not. Another 6/5 is 9. And 9 plus 6 is 15. Oh, that's good. 15/5, which is positive 3. Yay. Look at your partition. Your partition is no longer 1, 2, 3. Your partition are all these crazy fractions over here, right? You observe the way I got this partitioning. I got this by first placing down negative 3, which is the beginning of the world in terms of this problem. And then I kept adding delta x and recording those results. So negative 3 plus delta x is negative 9/5. Negative 9/5 plus delta x is, right, and you have negative 3/5. The goal is for this puzzle to fit nicely. By the time you get to your value at the end, it better be the previous number plus 6/5 to get you to the new number, and it is. So now what's the area approximated by? Our delta x is 6/5, that goes in front. And now I have function value computed at all these values. So it's f of negative 3 plus f of negative 9/5 plus f of negative 3/5 plus f of 3/5, f of 9/5. And this is where you have to be careful. If you start with the first number, you don't get to use the last. If you start after the first number, you use the last. You can always use only one end. And that should be common sense, because the way the rectangles work. If I draw a line at, let's say, x2, I can have a rectangle going this way, or I can have a rectangle going that way, right? So now think of the procedure we have for, let's say, square root. See over here, the value is 0, 1, 2, 3, 4. And observe, if I am at 0, the only rectangle that I can draw is to the right, which is actually on the x-axis, and that value is 0. But when I get to 1, I can draw a rectangle to the left or to the right. You have to pick one. And whenever you pick one, you have to use the same one for everything else. So if you are picking the one to the right, that means the point, rectangle to the right, point, rectangle to the right, point, rectangle to the right, and point, rectangle to the right. That's what it means. So in this case, we have a 0 area plus these guys. This is your first example. So now, so if I'm to do this, right, this is called the right hand sums, because the rectangles are to the right of the point you observe. To contrast this, you draw the same picture with the same 4 divisions. 1, 2, 3, and 4. but now you draw the rectangles to the other side. So you go from here. We already did this, but whatever. And you see that the one on the bottom has less error for this particular problem than the one on the top. One on the top has all of this over here as error. And this one has this big chunk, but then all of these are smaller. So that's if you are using the end point on the right, and you did because you created this rectangle here, then this point is in charge of this rectangle here, and this point is in charge of this rectangle here, and this point in charge is in this rectangle here. Now, if you draw the point over there, well, there's nothing on this side. Right? There's no function. So you can't create a rectangle on this side because it's the end of the road for us. So for this case, we didn't use the last point because we did use first one. For this case, we use the last one, but we can't use the first one. So it's always one or the other. So when you're setting up these guys, look, I use the first point. That means that I will not be using the last point. But also, let's use the common sense. If you have 5 rectangles, you better have 5 terms, because each term belongs to one rectangle. So 1, 2, 3, 4, 5. Stop. I forgot to close the parentheses, but that's that. So I already have 5 terms, and I just leave it at that point. So now we just need to compute this. X squared, great. So 6/5 x squared. I have negative 3 squared plus negative 9 over 5 squared plus negative 3 over 5 squared plus 3/5 squared plus 9/5 squared. And you have to close the parenthesis at the end because the 6/5 needs to multiply each one of these. Copy the 6/5. That's a 9 plus 81 over 5. Sorry, 25 plus 9 over 25. So 9, 81. Another one, 9 over 25. And now that's a 9/5, right? So 81 over 25. Yay! At least the denominators lined up. Apart from 9 in front, but we'll deal with that. So problem is x squared. It's 9 plus the fraction, common denominator 25, 81 plus 9, and then another 81 plus 9, so that's 280. Now these are the numbers that you can compute. This is a 5 over here. So we have 6/5 of, believe it or not, 3.14. Oh no, 314. And now you multiply by 6 and you divide by 5. So what's the quick way to multiply by 6? Is to add all of the values. So 6 times 300 is 1800. 6 times 10 is 60. And 6 times 4 is 24. So that's the fast way to multiply things. You break this into 300s, 1/10, and for right? Do I? What happened? Why?
81 plus 81 plus 18.
Oh, okay. I'm trying to see because I see something is off over here. Because it's not adding up because it was too small. All right. So I have 180 over 25. Plus 9. 16.2 times 6 divided by 5, 1944. There it is. What we are doing in this section is we are taking the shape, whether it's a trigonometric function, logarithmic function, square root function, x squared, whatever you can master, it doesn't matter. You create the rectangles, and when you have the rectangles, your partition, whether it's ones or halves or these crazy 6/5, right? You are going to have the dx when you're jumping from a to x1, x2, x3, x4, and then b at the end. Now, the more rectangles you have, the better precision, but then, again, more calculations. So you weigh the things out, and generally, on exams, we just want to know that you can do, basic stuff with 4 rectangles or 5 rectangles. So that's the way we deal with this. The only thing you need to know for this thing is the area of a rectangle, right? And then how to partition. So to put A and keep adding dx until you reach B. If you miss B, right, by adding dx's consecutively, well, something is wrong. Either your dx is wrong or you didn't add at one point correctly. It was easy earlier when your delta x was 1. What do I have? From 0 to 4 with the 4 rectangles, so 4 minus 0 divided by 4, that's 1. Delta x was 1, so 0 plus 1, plus 1, plus 1, plus 1, and you reach your b. When we did more precise version, over here, we had 4 minus 0 is 4 divided by 8 rectangles is half. So each one of the delta x's, which is the width of this, was half. So 0 plus half, plus half, plus half, plus half, 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 half. Eventually, we got to 4, and it stopped there. So that's the partitioning, right? So now we can take a look at what this is going to give us. Down the line. So now we can approximate any area under the curve with the knowledge that more rectangles is better precision, but at the same time more calculations, and that is obviously in some cases an issue. You also see that each individual rectangle is going to have delta x. So delta x can be factored out. And I did write somewhere over here like the general formula for this, where you factor out delta x. There it is. You factor out delta x, and then you just have to add all of the f of x's to get these things. All right. So let me just write this down. To obtain better approximation, use more rectangles. So that's the key. So for the general function that is partitioned between a and b, so this is some general f of x here, we are going to have a whole bunch of these rectangles as x1, x2, x3, x4, and so on. If we are doing the left areas, so AL, left area is going to be delta x, and since the rectangles are to the left of the point, you can't start at A. You have to start at f of x1 plus f of x2 plus f of x3 plus dot dot dot, concluding with f of b. If you are doing the right side, then your rectangle is on the right of the point. Then you are starting with f of a, but you will have no f of b on the other end. So either a or b are included, never both. And this is just I'm gonna call it xn because I don't know how many rectangles we have. But it's not going to be b. You are not going to use a b value. And we also add to this that delta x is computed as b minus a divided by n, which is the number of rectangles. So the book does a fair job at explaining all of this in words and more pictures. I just want to confirm that I have everything. Okay. So the last part of the first lecture is to learn about sigma notation or sum notation, which will be excessively used in Calculus 2. So, sigma notation. So, symbol sigma is a Greek symbol. That in mathematics represents sum. Now, it is very important to understand how this thing works. If I write summation, I goes from 1 to 4, and then over here I put I. If you ever programmed in life, you know exactly how this works. So just a loop over there. So when I is equal to 1, you will plug I equals to 1 there, and you will get 1. It is sigma, you put plus, and then this one updates and jumps up by 1. So I hope you can see that this is what you get. And you can't go past 4. So you start at the value that is in the bottom, and then you plug it in there. So that's 1. Plus, because of the sum, this updates to 2. Plug 2 in there. There is a 2. It's a sum, so it's a plus. This updates to 3. So this over here is the counter. I is the counter that will shovel through all counting numbers. You can start at 0. You can start at 1. So, well, you can start also at 17. It doesn't matter. You can start at any point. It's just important thing is that it's going to count without skipping from the point you provide as a start point and stop at the value that you provide is the end point. Let's take a look at some spicier examples. For instance, I have a summation where I goes from 1 to 3 of I squared minus 2. Great. You are going to plug in I equals 1 into I. You're going to get 1 squared minus 2 as the first term, and then you have plus. Your I updates to 2, so now you have 2 squared minus 2. And finally, the I updates to 3. So we have 3 squared minus 2. Now, compute. That's 1 minus 2 plus 4 minus 2 plus 9 minus 2. So it's negative 1. It's 1, 7, 8. Is it 8? Anyone? So 1 minus 2, 4 minus 2, 9 minus 2. Say? Thank you. So I'm going to challenge you with one of the summation ones. How about 3 I minus so we're just creating whatever formula. Minus I squared, I don't care. Counter is going to start at 2 and go all the way to 5. So try to compile this. Not compile this. Computer science mode. Try to compute this. Compile. Yeah, right. All right, let's go.
Is it ever used in a situation where, what if I don't want to use a conflict? But I just want to do something time-wise. So, for example, taking that last one as an example, I got some expression there after the summation that doesn't have I in it at all, but the summation just lets me do it. 3 times. I guess it would be 4 times. Yeah, because it's inclusive. I want to do something 4 times. I don't want Well, no, in the programming you have the loop. And you don't know what these are. Is that true in with this?
Yeah, but we don't need it. You can write out stuff, right? Because when you want to do something 4 times, just write 4 times. Right? If you want to compute,
100 times, you don't want to write that. You want to express something.
but I know, but you would use hundreds of times and then whatever you want to do. Right? Because that's what multiplication is. Because this is addition, and every time you want to do the addition, it is programmed. It is programmed. It's just that you are taking it too far. You need the counter, you play with the counter. We're going to actually play with it in a different way now. But let's just have people compute this.
Nick, you want back a tip? Wait.
I had coffee and just now.
Say, I'm not. But it's just like, I mean, you're going to be waiting for like a while. So I got two.
It was cake. Chocolate cake, ice cream. Can I take coffee?
I actually like it a lot.
Yeah, you put 2, 3, 4, 5. Yes, and then you carefully. Yeah. Yeah. No. Start at 2, 3, 4 times. 1, 2, 3.
What do you guys have as the answer?
Negative 17. Who said 406?
Who said negative 17?
Over there. I don't know. Is it? Why are we talking? Eddie, what do you got?
At least I tried, guys.
I don't know what it is.
I don't know either, that's why I'm scared.
Yeah. So you are replacing i's. First time around with 2, second time around with 3, and then 4, and then 5, and just add the parentheses. And then carefully compute. So what do we have? The first, so I'm going to have 4 parentheses here that are added. First parenthesis has 3 times 2 minus 2 squared. Next one has 3 times 3 minus 3 squared. Next one has 3 times 4 minus 4 squared. And the last one has 3 times 5 minus 5 squared. So now we compute. 3 times 2 is 6. Minus 4 is 2. Plus 3 times 3 is 9. Minus 9 is 0. Plus 3 times 4 is 12. Minus 16 is negative 4. And 3 times 5 is 15. Minus 25 is negative 10. Negative 12.
I did wrong multiplication. I was so close.
You did wrong multiplication?
Yeah, so
I'm so interested in which one.
the last one is
Oh, 3 times 5?
is 15 minus 25. Instead, I did like 15 instead of 10. So I got negative 17, but I was so close. I did it right up to the.
Alright.
Yeah, that's fine. At least I got the concept.
The last summation that I want to say is you can use it this way as well. You can use the counter in index. So I can say xi, where I goes from 0 to 6. This one is not going to compute anything. This one is you're just going to write it out. These i's, the counter now, is in the index. So you have x0
plus x1 plus x2 plus, who went all the way to 6? Plus x to the 4 plus x to the 5 plus x to the 6. That's it. Let's go home. So it's much easier to write this thing, especially if you want 100 terms. You go from 0 to 99. That's 100 terms. You see that it is... So we don't get to compute anything because I don't have the values for this. I don't have the values for this. But let's do something cute and tie it to what we had before. Remember how my partitioning, and we'll take the easy one. Remember how my partitioning went 1, 2, 3, and 4? So this is my x0, x1, x2, x3, and x4, where x0 is A and x4 is B in this example. So now, as I look at this, I can rework the formula. Let's say area, do you want to do left or right?
Left.
Left. The left one will have the rectangle to the left. So that, AL. So we agreed that that's going to be delta x times, and now you have f of x1 plus f of x2 plus f of x3 plus f of x4. F of x4 is f of b, right? See, I can condense this now because these values on x have a counter x1, x2, x3, x4. I can compress that into summation of xi, and I let the I go from 1 to 4. So that's much shorter way to write the thing. And there is multiplication in between these two. So what I'm going to do now is I'm going to swap the order. And when I swap the order, I get summation. I goes from 1 to 4, xi times delta x. Oh, guys, sorry, I forgot f. F of xi. I'm looking at this to say, there we go, f of xi. So it's f of x1, f of x2, f of x3. There we go, much better. This is going to approximate. This is the same thing we did already as example 2, I believe. This is example 2. Written in the compressed form, in the sum notation. Written in the sum notation. Clearly, if you want to compute, you will use the expanded form. You can't compute from here. But at least, you know, it's nice. It's also nice to know something like this, to write it on a napkin, as, you know, as someone is trying to talk to you, right? Put that on a napkin. And this is the end of 5.1. We have
we learned a little bit about the summation notation and that it's used to compress these long expressions into shorter notation. And the entire lecture on approximating area under curves is summarized here in the red, where you know how to get delta x and you know these things. So now you know that this part over here can be written as a sum. Right? That's the benefit of shorter notation.
What are we going up to? 5.5?
5.5? What happened?
Huh?
What happened? Good.
So the quizzes start tomorrow, right?
Yes. Is that okay with you?
That would be great.
I mean, we can delay it 3 days and then have 2 each day.
That was like big anxiety. I like kept checking.
So let's quit this one.